rare, localized intense structures. This is the magnetic field produced by chaotic, not random, but chaotic Gaussian, Lagrangian chaos magnetic field. On the right, I show the Gaussian random field with precisely the same spectrum. The spectrum of these two fields are exactly the same. So the only thing which is changed when moving from the left-hand box to the right-hand box is that the phases of the Fourier modes have been randomized. This is the result. The spectra of these fields in these two boxes are identical by definition, by construction. But this is the probability distribution function of these components of this vector magnetic field. This is on the right, almost perfect parabola, meaning Gaussian distribution. And this is the PDF on the left. You see these heavy tails. This is the signature of deviations from Gaussianity and very often a signature of intermittency. So if I want to understand and characterize this field in the left-hand box, Gaussian statistics is definitely not sufficient. Of course, I can always press the button on my keyboard to get fast Fourier transform. I will get a spectrum, but this spectrum will tell me virtually nothing about the structure of the field in the left-hand box. I need something else. And there is not much else that we can use. So what people do in such cases, they start considering higher order statistical moments. And then it's well known how these statistical moments scale with n for a Gaussian random field. And then deviations from Gaussianity are characterized by the deviations from the behavior with n expected for Gaussian random fields. But first, there are infinitely many statistical moments. Second, as n increases, the accuracy of this of calculation of higher order statistical moments decreases just catastrophically. It's not a coincidence, I think, that in a vast majority, not all, but vast majority of papers where people publish these higher order statistical moments from either simulations or observations, they very rarely plot error bars on this, even though error bars can easily be calculated. If they did, the picture would be different. The error bars increase with n catastrophically. It's not a solution, or it's only a partial solution. So, very often, random fields that we encounter in astrophysics or cosmology are non-Gaussian, intermittent, and they're topologically non-trivial. For example, in applications to cosmological random fields, galaxy distribution, large-scale structure, Euler characteristic, a topological characteristic, is regularly mentioned. Is it the only one? Is it Euler characteristic? Is it the only topological characteristic? Of course not. What are the others? So, the better data we have from observations, the better computers we have, the more attention will be there attracted to non-Gaussian properties of the random fields that we either observe or simulate. How to describe them, how to compare them. If I have two simulations where the result has strongly non-Gaussian statistics, how I compare them? How can I decide if these two simulations are compatible with each other or not? Or how can I decide if my model describes observations well enough if I cannot rely on Gaussian statistics? And there are not many tools which go beyond Gaussian statistics. And computational topology is the area of research which only emerged relatively recently, sort of 10, 15 years ago. And in one of the best books on the subject of Adler. He writes very good books. He explains things very nicely. There was quite a remarkable statement in that book. What he writes there is that now there is a breakthrough in topology. It happened because topologists stopped admiring the beauty of their subject and decided to do something useful. And I want to discuss that breakthrough. I want to discuss what useful can we get from topology. There are a few references. Well, here in this paper in Journal of Plasma Physics of Irina Makarenko et al., we tried to present a review of these methods written in a language accessible to humble human beings like myself. Because it took for me quite an effort to try to understand the topological texts, which are as dense as many other pure mathematical texts. So to save the effort of other people, we prepared this review in Journal of Plasma Physics, which perhaps will be helpful. And I will try to explain the main ideas of these methods in a human language. But please, by the way, do interrupt me with your questions. I would appreciate having questions as we proceed. So, what's the problem? Here, there are two snapshots from our simulations of the interstellar medium. These are density fluctuations. Yellow means high density, black means low density. These are fluctuations, so the mean has been subtracted, so they can be negative. And we had this distribution of gas density is obtained when magnetic field in the system is very weak. This, when the system has generated by the dynamo action a mean magnetic field. You can see the traces of it. First, you immediately see that the distribution has become anisotropic. This is because of the mean field, imposed mean field. This is easy, but there must be other differences. What are the other effects of magnetic field on the system? How can I decide? And again, normal instinct is to look at the correlation functions. It's a random function. Use the correlation function. Here are the two correlation functions of those two boxes, almost identical. Again, look up. So in the next slide, the correlation functions are obtained for exactly these two boxes. Here they are. What should I do? How I characterize this? Obviously, I can see with my naked eye that the two random fields are different. Correlation function doesn't help. More examples from the same simulation. So these are just two different positions within the same box. This is near the mid plane, or this is a model of galactic disk. This is the near mid plane. This is higher up in the galactic halo. I see here that the structure of these random fields not only depends on magnetic field. Here it is weak, here it is strong. Here it is weak, here it's strong. But also on the position within the box. Again, I can see with naked eye that these two random fields do look different. But the correlation functions are almost identical. There is some difference. But I know I don't trust that the difference I can see at a correlation function can capture all the difference between these two random fields. And in this case, even the difference between the two correlation functions, as I showed in the previous slide, is statistically insignificant. So this is where I became interested in this topology and other measures. I wanted to understand the random fields which are coming from my own simulations. And it was quite clear that the standard tools of analysis, which fully rely on spectra or second-order moments, are simply not sufficient. Then the main tools of the computational topology relies on what is known as Betti numbers and persistent diagrams, which are the way to represent these Betti numbers. So I want to define in a slopey way, without introducing rigorous definitions and theorems. Let's consider a d-dimensional random field f position, depending on position. Well, you wouldn't lose anything if you make d equal to 3 or 2, three-dimensional or two-dimensional velocity field. Then let's draw either surfaces or either contours of your random function. So either surfaces at the level h, and it's convenient to measure the level in terms of the standard deviation of your random function. So h is dimensionless. It's dimensionless level of an either surface in 3 dimensions or either contour in 2 dimensions. Then I will illustrate this with a picture in the next slide. Then there will be some clouds in my distribution of these either surfaces. And the number of such clouds is called Betti number 0. Number of holes gives me Betti number 1. And number of unshrinkable, well, holes mean holes in 2 dimensions. In three dimensions, these will be closed contours. In 3 dimensions, they will be closed surfaces, voids. Exactly the same voids as people talk about when they talk about the cosmic web. These are exactly those voids. It's the Betti number 2. The number of Betti numbers is equal to the number of dimensions. In 2 dimensions, there will be only 2 Betti numbers. They will be only connected components and holes. In 3 dimensions, there also will be voids. And remarkably, the Euler characteristic, familiar Euler characteristic, is just alternating sum of the Betti numbers. So if you wish, Betti numbers decompose the Euler characteristic and go deeper and deeper and deeper into the structure of your random field. And then another problem with random fields. Well, basically, they have infinitely many degrees of freedom. We need to simplify them. We need to compress that information contained in the random field in the same way as MPEG compresses the audio signal or video signal with some loss, but still trying to retain important features. And this is achieved by the process called filtration of a random field. So the purpose of this is to reduce the amount of information that you get in the random field and only focus on important features, not random insignificant noise, even though noise can also be significant, it can be physical noise, but still, we want persistent features, important features. So what we do is the following. Let's think about 2-dimensional field. Replace this D by number 2. Let's scan it from the bottom. Let's say in any finite domain, there will be a minimum and maximum value of f. Let's consider either surfaces at the level h and focus on the interior of such other surfaces. And then increase this h, scan the field from bottom to top or from top to bottom. If you wish, we have a landscape, mountainous landscape, and we start moving a plane down and looking at what islands we see above the sea level. The sea level decreases. As it decreases, we see more and more islands, and we focus on those islands. This is what we are doing here. Then each island will correspond to Betti number 0, a component. Each hole, a lagoon, a lake, will correspond to Betti number 1. And these Betti numbers will change only when my sea level will pass through a maximum, top of a mountain, or a minimum bottom of a valley, and different islands can merge when I pass through a saddle in this f of x. And then I will record these Betti numbers, number of components and lakes, islands and lakes, and I will characterize my random field in terms of the dependence of these Betti numbers on the level. So at every given level, how many islands and how many lakes I have, how this changes with the sea level. And then this representation of my random function in terms of the Betti numbers is called filtration. So it can be confusing. The result of the process of filtration is also called filtration. Only pure mathematicians can be so negligent about language. So both process and result are called with the same word. So an example, this is a two-dimensional Gaussian random field. Blue means a minimum, red means a maximum. So I choose a very low level. So here is the sort of three-dimensional representation of it. And I scan it from below. So my sea level is minus 1.25. Then I will see here an island here, another island here, another island here. These are the components, clouds. Then I will increase the level. What will happen is that two minima will have merged. There is a saddle in between, somewhere here. Through that saddle, they have merged. The other structures have increased. New structure has appeared. This minimum, which is somewhere here, is a bit higher. Therefore, it didn't occur at low level, but it emerges here. Go further up. Some structures remain, the others merge, new ones appear, and here a hole appeared. It's this hole here through the saddle, and so on and so on and so on. And then I go up, some holes disappear. This is what we are doing. So, and this level, I count the number of components, the number of holes, and then what I do, I present these results in the persistence diagram. So there will be a level when a given structure appears. It's a hole or component, and then there will be a level V where it will have disappeared. And then I will represent my data in the UV plane for each of the Betti numbers, separately for the structures, separately for the holes. And this is what is called the persistence diagram. Here are persistence diagrams for the simulations I was showing you before. So these are the components, clouds, and these are the holes. So there's a diagram. This is birth. This is death. If the level of birth is equal to the level of death, this means it's a very ephemeral, very short-lived structure. Some small wiggle, perhaps unimportant. So the diagonal is important. On the diagonal, there will be those structures which are very short-lived. Part of this is just statistical noise, but part can be physical noise. It can also be interesting. But then, look at this. There are also structures which are very pronounced. They are persistent. And these are very often are the most physically important structures. So this is how it works. I scan the field, my random field. I record the Betti numbers. But by the way, all the methods, computational methods to calculate all this stuff, Betti numbers, persistence diagrams, are very well developed and readily available in this statistical package R. There is a library called TDA, Topological Data Analysis. Very good library. And I think many of these tools are already available in MATLAB, for example. I won't be surprised if Python either already has something similar or will soon have it. So there is no need to write your own codes. It's like for fast Fourier transform. You don't need to write your own fast Fourier transform. There are libraries available. Likewise, for topological data analysis, very good libraries are already available. So this is a weak magnetic field, and this is a strong magnetic field. We do see the differences, right? We do see that this topological analysis does capture some differences between the cases of weak and strong magnetic fields where the correlation analysis failed so badly. But then the question is, how can I compare these two distribution clouds of points? How to compare them? The standard method developed in the area of computational topology relies on what is called bottleneck or Wasserstein distances. Basically, what they do, they introduce the measure in the space of clouds of points and test this method of these distances in sort of artificial examples, like, for example, a photograph of pebbles on the beach, to see if these diagnostics can distinguish big pebbles from small pebbles. It works there, but when we try to apply these standard methods, standard diagnostics, to real fields that we had, they didn't work. They turned out to be too blunt instruments for more realistic random fields. So I will discuss now what is our experience, what worked for us. Well, it doesn't mean that what works for us for our random fields will work for all random fields. We never tried to be generalistic. The more so that this area or these methods are developing very fast. New methods appear, new approaches appear. So we are approaching, I will be discussing what worked for us. So one thing which worked is the total number of cumulative Betti numbers. This means the total number of components or total number of holes in the distribution across the whole range of parameters. So this is what I plot here. This is our simulation. Time increases in giga-years, and as time increases, magnetic field in our system grows. And this is where I started. I could see that the magnetic field does affect the gas distribution. These are Betti numbers, cumulative Betti numbers, for the gas distribution. And I want to see how they change between two states of the weak magnetic fields and strong magnetic fields. And indeed, I can see the very significant difference. Unlike correlation analysis, here, Betti numbers are sensitive to the presence of magnetic field. But then there is a sneaky suspicion here. Okay, it does change, but topological changes are not the only changes in the random field. These are Betti numbers per unit area. But 1 kiloparsec or 1 megaparsec or 1 centimeter is our arbitrary measure. Why should we use our arbitrary unit of length to characterize a physical system? Shouldn't we better use the length scale intrinsic to the random field we discuss? So then the idea is to calculate Betti numbers not, or any other variable, not per unit area, but per area or volume of the correlation cell, the intrinsic scale of the random field. Now, there is quite a number of applications here on the bottom. There are references to applications of this method to cosmic web. Invariably, Betti numbers there are considered calculated per unit volume. I don't know how important it is in their case, but in our case, the using unit area of volume would be misleading. So this is a repetition of another copy of the slide of the plot you saw in the previous slide. These are Betti numbers per unit area, and you can see that they increase as magnetic field becomes larger. So more components per unit area, more holes per unit area. But now these are the same numbers, but calculated not per unit area, but per correlation area. And remarkably, they are dimensionless, of course. And now, all of a sudden, you see that the trend is opposite, because the correlation length has changed due to the magnetic field. The difference here is statistically significant. We checked it. So just to give you the measure, the typical values of maxima or minima per unit per correlation cell is 0.6 to 0.4. Just for the reference, for a Gaussian, two-dimensional Gaussian random field, the number of maxima or minima per unit area, per correlation area, is about 0.5. And the number of saddles is twice as large. There are the sum of the number of maxima and minima is equal to the number of saddles for a Gaussian random field. So this is just as usual, Gaussian random fields remain our reference point. K here is the autocorrelation function of your Gaussian random field. So 0.45 obtains for a Gaussian random function, for a Gaussian correlation function. So I suspect that the difference between simulations with weak and strong magnetic field can be because of the difference in correlation length. And indeed, this is the correlation length as a function of position within my box. That is the distance from the midplane when magnetic field is weak, and this when it's strong. Here at large heights, there is little difference, but at small heights, the difference is very large. The correlation length has changed by a factor of more than 2. The correlation area has changed by a factor of 4. This is why the Betti numbers per unit area per square centimeter can be misleading. Here, as we saw here, at large heights, 0.5 kiloparsecs, the change in the correlation length are negligible. And the two pictures per correlation area, per unit area, are very similar. So this is a lesson which I think is important. Correlation analysis remains an indispensable first tool in any analysis of random function. So first, when you have an Gaussian random function, first look at the correlations, look at spectra, look at autocorrelation functions. But don't stop there. This will be a useful knowledge, but you need to go further. And then the important message for me was that Betti numbers have physical meaning when they are scaled to the intrinsic length scale of your random field, not to an arbitrary length scale. In other words, a trivial statement, it's better to work with dimensionless quantities. Betti numbers per correlation area of volume are dimensionless. Betti number is dimensionless. Per unit area of volume are dimensional. Better to work with dimensionless quantities. Trivial statement, but I forgot about it myself, and I think that very often we do forget about such simple things. Now, what else can we do? How can we compare these clouds of points in persistence diagrams? And here we worked with Rob Henderson, who is a professional statistician and a very good one. to trying to develop statistical approach to these topological diagnostics. They are very underdeveloped. Statistical analysis, statistical tests, well, Kolmogorov-Smirnov test, chi-squared test, most of them have been developed for Gaussian random fields. And there are not many such similar statistical tests for things like these clouds of points. So I will explain why, but this is like an abstract. We confirmed again that the standard measures, these distances between persistence diagrams, which have been developed in topology, rarely worked for us, very rarely. We found, it's not an exclusive list, but at least we found that cumulative Betti numbers are informative. And also, I will explain what does it mean. Convex hulls on persistence diagrams were informative. And then we combined the two statistical measures together, and I will tell you now how it worked. So what we did, again, we prefer to be specific, and we selected the gas distribution of the Milky Way, H1 distribution. This is the brightest temperature. This is galactic longitude. 0 means galactic center. 300, 200, 180 means anticenter, somewhere here. And this is latitude. It's relatively high galactic latitude, minus 40, minus 50 degrees latitude. And we have selected 3 regions in this strip. And I should say that we deliberately were selecting these 3 regions just from their appearance. We wanted to have some interesting structure in them. And the question was, shall we be able to distinguish between the random fields in these 3 boxes? And we absolutely deliberately, by design, we were not looking into the astronomical significance of these regions. We were not looking at where are the arms, star formation deliberately. We wanted to know if these methods will be able to identify anything unusual, astronomically unusual. It was easy because Rob Henderson is a statistician. He wasn't interested in astronomy at all. He was interested only in statistics, which was in this case very good. So 0 astronomical input can we formally tell if these 3 regions of fluctuations in H1, this column density of H1 here, are they similar, are they different? And after that, check if your conclusions will agree with astronomical data. So it's an acid test, if you wish. So we have a persistence diagram. How to characterize this shape? And we found that a useful approach is the following. Draw a convex hull of the points at a given level. For example, this hull contains all the points which are here on this diagram. Then take 99% of points. Then this point will go, the one which is the farthest away, and then this hull will contain all the remaining points, these ones, and continue, go further and further and further, and this envelope contains 90% of points. And just a trial and error, it seems that 90% is as good number as any other one, at least for persistence diagrams that we had for H1 observations. These are real H1 observations, which I showed you in the previous slide. This 90% is a number good enough. Now I want to characterize the shape of this hull. And for this, we use filamentarity. Filamentarity is defined, it's related to Minkowski functionals, and I think we're very familiar in IUCAA, where Varun Sahni was contributing so much to developing this tool. P is the perimeter of this contour. A is the area enclosed by this contour. So perimeter squared minus 4 pi a, perimeter squared plus 4 pi a. This quantifilementarity is positive definite, it's less than 1. For a perfect line, it's equal to 1. For a circle, look at this for pi. For a circle, it's equal to 0. So the larger is f, the more elongated is your structure. Now, these are our 90% peels. Red line is for region 1. I showed you these 3 regions, right? Red line is for region 1, dashed line is for region 2, and blue line is for region 3. These are number of components, number of holes now. Same picture. Region 3 stands out. Regions 1 and 2 are very similar. Region 3 is slightly different. Next, these are cumulative Betti numbers. So it's like cumulative PDF. Again, regions 1 and 2, these 2 curves are very similar, but region 3 stands out. So we have identified these 2 measures as most informative, where the difference is the most significant. And then what you want to do, you can combine 2 tests, 2 hypotheses. My first hypothesis, null hypothesis, is that these distributions here are identical, and this distribution's second hypothesis are identical. These are 2 null hypotheses. So I want to combine several hypotheses into one test. And there is what is called Bonferroni correction. To avoid incorrect rejection of the null hypothesis, if you want your result to significance alpha, say 95%, then each individual hypothesis should be tested to a higher accuracy. Alpha divided by n. No, the other way around. Alpha is 0.05, 5% significance for rejection. Then you have to test each individual hypothesis tighter with higher significance to achieve a given significance for a number of hypotheses. I liked it. I never, before that work, I never knew about this very useful statistical tool when you combine many tests together. And then, indeed, we could confirm that regions 1 and 2 are similar, and moreover, they're consistent with Gaussian statistics. We compare it with synthetic Gaussian fields, but region 3 is different from them. We confirmed this using Wilcoxon test. And then, only then, we looked at the astronomical features. Unlike regions 1 and 2, region 3 contains the Orion Iridium superbubble, so the site of strong star formation, shock waves, stellar winds, and so on. So the acid test has passed, at least in this case. With 0 previous knowledge, we have identified a region 3 which is astronomically significant among those 3 regions. Well, come on. Of course, we knew that star formation makes interstellar medium different. My aim is not here now, is not obtaining physical conclusions, new physical results. My aim is to develop and test statistical methods to analyze complex, non-trivial random fields. So, what can we say in total? It's my last slide. First, correlation analysis. We need more than that, even if we use higher order correlation functions to characterize realistic, non-Gaussian, intermittent random fields. Among very few methods which do not rely on Gaussian statistics and are sensitive to all statistical moments simultaneously, are topological measures, such as Betti numbers. But the standard measures developed in this area did not work for those random fields that we were interested in. What worked for us, at least, was the filamentarity, the shape of these convex peels of persistence diagrams and cumulative Betti numbers. This worked well enough for us. Moreover, Betti numbers should be calculated per correlation cell rather than per arbitrarily chosen unit area or volume. This, I think, is important. And then, of course, on the way, we discovered quite a number of physical results, which were not in my focus today, but still, we discovered, for example, the effects of magnetic fields on the interstellar medium, which would be impossible or difficult to get with correlation analysis alone. Correlation analysis remains an important feature. For example, we found that magnetic field reduces the correlation length by 20-30%. This comes from standard correlation analysis, just integrating the autocorrelation function. But we have discovered that magnetic field makes the interstellar gas both more spongy, more small holes, and yet more filamentary. Gosh, just imagining how this can be true and how to imagine the two random fields, which are both more spongy and more filamentary, is difficult even to imagine. You cannot do it with naked eye. You cannot do it by just looking at colorful pictures, however good is your color scheme, or even movies. You need quantitative tools to find out such results. And then another more or less trivial result, which you can get without any topology, magnetic field makes everything more homogeneous. It just adds additional pressure, so this is easily understandable physics. So I think that these topological methods are powerful. They are sensitive to physical features of the fields. The tools, computational tools for them, are readily available, and I think they have a big future. Try them. Try them. If you have observations or complex simulations, try them. Try TDA in R package. It's very good. Look at MATLAB. And it's a pleasure to work with them. It's interesting. That's it. Thank you.
Thank you, Anvar. Thank you. So great. Nice to hear all about the Betti numbers again, a little bit more. And yeah, every time I hear it, it looks more complicated and quite
complicated. I'm telling you, Kando, there is, it's like fast Fourier transform. The algorithm can be arbitrarily complicated.
Yes.
But application is not. Using it is not complicated any longer, right?
Yes. Correct.
So in this sense, but then this is what I tried, to do. We are exploring. It's one of the things which can, because again, the problem is difficult. You want to characterize the cloud of points. It's a non-trivial problem. We are exploring. This is where it gets complicated. But otherwise,
yes. Yeah. So questions people can please raise their Zoom hand and ask questions. Yes, already 2 questions. Dipanjan, can you unmute?
Yes, Kandu. Hi, Anvar. Sorry, I missed the first half of your talk, so I may sound a bit ignorant because I was in a different meeting. So I'll go back and read your paper
and
more.
No problem.
A great talk, and this last example that you showed, comparing without knowing about the astrophysics, the 3 different slices and finding that there is some difference. It was remarkable to see. I wanted to understand if we do want to inject some physics or astrophysics and test that inside the topological model, where would you inject that?
This is a difficult question because most texts about this topology, they do say that physical interpretation of these Betti numbers is vague, which is true. But we should do something. We should start developing this physical understanding. For example, for me, maybe I'm too naive, but I treat this Betti number 1 as number of holes and Betti 1 as number of clouds. What's unphysical about that? To me, they do have some physical meaning. Plus, Betti number 2 in 3 dimensions is just a number of voids. So, how to connect, for example, a change in Betti numbers, for example, here, to the appearance of the picture? It can be more difficult, but it may or may not be a problem. It can be that here this quantitative analysis captures something that even your eye cannot capture easily. Then it's an advantage. Then, of course, it will be difficult to interpret these quantities physically, because physically, at the end of the day, means as my eye can see it, right?
Yes, that's right. Right.
And then maybe it's an advantage rather than disadvantage of these methods, that your eye cannot quite see it, and yet there is indication. But again, we all know that we should never accept anything where our eye doesn't believe it. You have to go deeper. One has to understand deeper what features in the physical field corresponds to these changes. But it's a process of development. I cannot say that I have all the answers. Right. I have very few answers. I have more questions like you.
Yes, okay. Kandu, I have another question, but I'll wait for the end, maybe.
Yeah, no problem. Okay. Dipankar, can you go ahead?
Yeah, my question is not unrelated to what was just asked and what you described. So suppose we look at this persistence diagram and the filamentarity of it. Right. So, what would it mean about the distribution if it happens to be more filamentary or less filamentary? We have to invent new words for these descriptions.
Yeah, more filamentary would mean that, since it's always the case that most points are near the diagonal, and the diagonal are the most short-lived, less important components. So more filamentary means stronger noise and fewer points away from the diagonal. This would create for you a more filamentary structure. But here's the caveat here. When I say noise, there can be statistical noise, which is a burden. You want to minimize it. There is physical noise, which comes from turbulence, for example, which is informative. And then not only the filamentary, but probably the shape of this hull contains some information about beyond the spectrum of turbulence and stuff like that, just this shape. I cannot know, it needs to be investigated, but more filamentarity means stronger noise, basically.
Stronger noise, yeah. Thank you.
Thanks, Anvar. Axel, can you go ahead?
Thanks, Anvar, for your very interesting talk. I very much enjoyed it. The persistence number indicates obviously some change with respect to time. Now, my question is, there are certain changes that could involve certain spatial translations or transformations, rotation or translation, for example. To what extent can the persistence number take that into account, like a systematic swirling of in the motions, for example?
As long as topology doesn't change, nothing will change. If I take my box and turn it, topology remains the same. But Axel, persistence here means persistence in the space of levels. It's not in time. So the most persistent structure will be the one which corresponds to a very deep or very high maximum minimum. So, for example, look at this. At this point in the upper left corner, it is born at very low level, -4, the lowest close to the absolute minimum, and dies at +4, absolute maximum. There will be always one such structure in the corner, which corresponds to the full range of levels. And this is not interesting, it's trivial. It's always be there, a point in the corner. But what is important is now how other maxima and minima are distributed, how frequent they are, where they occur. But these are topological things. Translation, rotation, compression, shear will not change anything. It may be disadvantage. Depends on what questions you want to answer, right?
Yes. Yeah. I mean, that's another question. And of course, what does one miss by looking at the persistence diagrams in terms of exactly such features that are still important for magnetic field generation, right? If you have locally something swirling, that's tremendously important. And it's not.
If swirling is important, take the curl and apply these methods to the curl. Then you will focus on persistence in curl, right?
Okay, so you would look at the persistence number of simply a different quantity.
Different quantity, yeah. This is what we did with Minkowski functionals, for example, when we were studying the structures in magnetic field. Then we also looked at structures in the current density and structures in the velocity field and compared all three.
Right. So so you want a scalar. Each time you do a persistent diagram or the Betti number, you need a scalar. So it's not just one component of the velocity field. Is it either the maximum or the modulus or the entropy? These are the quantities, right? So meaningful scalar quantities that you derive from your vector field.
This theory has been developed only for scalar fields. We had a grant where I, in absolutely cowboy way, promised that we shall explore extension to vector field. We tried, but it was difficult. It is difficult because there is no theory. All this topological theory developed by pure mathematicians is only for scalar fields.
Yes. And do I understand correctly that in order to do that persistent diagram, all you need is simply just the Betti numbers for all the different snapshots? Yes. So it should be a standard procedure that should have been implemented into the pencil code already. It's not probably, right?
Yes.
But Axel, I think the easiest could be linking pencil code to R. R is an open source packet.
Yes, okay, right? Sure. If somebody can help me with that, would be good.
Let's discuss it.
Yes. Okay, good.
Okay, great.
Thank you, Anvar.
Thank you, Axel.
Let Shivkumar, can you unmute and ask your question before?
Yeah, great talk, Anvar sir. I have a small question. So if I start from small scale, initial small scale turbulence and evolve my say simulations over time, okay, and take snapshots in different points in time and analyze the persistence or Betti numbers, will I see some kind of a pattern in the Betti numbers? Like say in the initial stage they are more, and over time they become lesser and lesser as larger and larger structures start forming?
I would think so. At least look, when we tried it with our simulations where there was some change in time. It doesn't matter what change in time it was. In this specific case, magnetic field was increasing. Magnetic field was weak here, strong here. Otherwise, the system hasn't changed. Yes, I think this is exactly what we were doing, checking how the system changes with time, because I know that some physical features of the system do change. I would think so. But again, if you have a weak turbulence or Mach number is very small, so the flow is nearly incompressible, then deviations from Gaussian statistics are only mild. Well, if you read books about turbulence, right, very often they write a special section about deviation of Gaussian statistics, even in Kolmogorov turbulence. There is some intermittency, but it's relatively weak. But there are cases where deviations from Gaussian statistics are strong, and then these Betti numbers become important. Have I answered your question or not? If not, let me know. I will try better.
Sorry. You got, he got muted again.
Yeah, sorry.
Has he answered your question or not?
Yes, sir. I have. My question also stems from the fact that as I move from, say, random magnetic field, random small-scale magnetic field, to larger and larger magnetic fields. Say, in my case, I use helical turbulence. I would start getting inverse cascade and generate larger and larger structures.
Yep.
So in that case, will there be? Will I be able to capture some kind of a current sheet mergers? That's the key point.
I would think so, because if you have a large-scale field growing, right, then in the sense of percolation theory, for example, this means you are changing the topology, for example, of the isosurfaces of B squared. So it's easier to talk about scalar quantities, exactly as we discussed with Condon just a minute ago.